In this video, I'm going to focus on forces that are angled in their direction. Let's start with a sample force diagram over on the left. It doesn't really matter what these forces are. I'm just calling them F1, F2, and F3. But the important part is F3. You can clearly see that it's angled relative to our X and Y axis. The dot in the middle represents the object. And just know that this object is known to be motionless. So the goal here is to come up with usable equations in the X and Y axes, trying to explain why this object is motionless. I'm going to run you through a couple wrong ideas first. Wrong idea number 1 says that F1 plus F2 equals F3. This is incorrect because of direction. F1 is in the x-axis, F2 lies on the y-axis, and F3 is angled. It's in both the x and y-axis at the same time. So I cannot compare forces in different dimensions. I want to make sure I'm only comparing forces that are on the same plane. The next wrong idea is a little better, but still not where we want to be. Some students might think that since F3 is in both dimensions, you can simultaneously set it equal to each of F1 and F2, but we still have a directional problem. We can only compare forces that are on the same plane. Although F3 is in both dimensions, not all of it is X and not all of it is Y, only some of it in each plane. So I can't just set it equal to both. We again have a directional problem. So what can we do? Here we want to introduce component forces. This is representing how much of the vector F3 runs to the right, that's F3x, and also how much of vector F3 runs vertically upward, that's F3y. These are the things we're going to want to use in our equations because they represent only how much of F3 is in each plane. So I'm going to set F1 equal to F3x, I'm going to set F2 equal to F3y, and notice that F3's overall value is not included. You're going to use F3 up to find F3x and F3y, and those are the things that end up going in your equation. A sample problem, I'm going to talk you through it. Here we got a box at rest. There are two ropes keeping it at rest. One of them is angled here to the left, another one horizontal, connected to a ceiling and a wall. The goal is to talk through a force diagram for this scenario. Step 1, let's identify our object. We're doing forces for the box. From there are three forces present. I have a tension force directed up and left from the angled rope. I have a second tension force directed straight to the right from the horizontal rope, and I have a gravitational force directed vertically downward from the earth. Now, something to talk about here is when you have multiple forces in the same force diagram that are similarly labeled. So 2 FTs in this problem. Something you might want to add is a subscript. I just chose to do FT1 and FT2. You can make it FTA and FTB, whatever works for you, but just try to differentiate between them with an additional label. From there, we're going to draw in our component forces. You're going to want to do that for any angled vector. So FT1x represents how much of FT1 runs left, and FT1y represents how much of FT1 runs upward. From there, I use the components in my equations. I've got FT1x equal to FT2, and I've got FT1y equal to FG. Again, notice that FT1 itself does not appear in either equation. One more example, this one for you to try. First one we've seen with two angled ropes. See if you can complete a full force diagram. If you want to pause the video and run through it, I'll talk you through the steps here shortly. And so we circle our object at the top right. We have three forces, FT1 up and left, FT2 up and right, and FG straight downward. Because we have two angled forces, we'll need two component triangles. So I've got FT1x and FT1y on the left, FT2x and FT2y on the right. In my equations, there are only two horizontal forces. Those are the x values. I'm going to set them equal. And vertically speaking, I'm going to add the two y components together since they both point upwards and set that equal to the downward gravitational force. So in summary, if you see an angled force, you can consider making a triangle out of it and establishing an x component and a y component. And those components are what go in your end equations.